So today we are just going to continue. Well, we intend at this moment to show the same expression we obtained last time, which we called the landmine achievement. One of our expressions for the Christoffel symbol. Okay, so well, we intend today to use an affine connection formula. Normally in our affine connection, this place, if you can look at this expression here, this is usually placed with the z prime of x. Now we're just going to replace that z prime of s with some x prime. And we intend by this method, therefore, to find the same expression. So let's just move on and see if, well, this method is going to make it seem like it wasn't that much of a landmine achievement after all. So just depending on the method. But regardless, it's still something very important, and so it's worth considering another method towards this. Okay, now, so proceeding as we should, here is an expression for the metric tensor, maybe in some non-inertial frame, being transformed or related to a metric tensor in an inertial frame. Well, this could be some eta sub mu. But for now, let's just call it G mu nu prime, as we have written over there. So, given G alpha beta to be equal to the x prime mu, the x alpha, and the x prime nu, the x beta, with here G mu nu prime. Of course, here we want to find this, treat this G mu nu at this moment with as some kind of constant. That, for instance, will be the best part for us. So, which is in particular why we are considering it to be the metric tensor in some non-inertial frame. So, at this moment in time, supposing we say something like differentiating this G alpha beta with respect to x gamma, which is the same as this alpha beta comma gamma. Now, this will be the same as, of course, usual Leibniz rule. I'm going to say the 2x prime mu, and here the x gamma, and here the x alpha. Then I have the x prime nu, the x beta, G mu nu prime. Next, I'm going to have plus. I just leave the first differential untouched, the x alpha, but then the 2x prime nu, the x gamma, the x beta, G mu nu prime. So in this expression, we have all along kept G mu nu prime a constant. Now, as we proceed, again, of course, given our definition of the affine connection, so this was actually designed to look just like what we will need in the end, but it's fine. The x prime mu, and this is the 2x prime mu, and here the x gamma, the x alpha. You can see that if I multiply both sides by the inverse of this differential here, that's by saying the x prime mu, the x nu. In other words, this entire expression, if I multiply it by this, the x prime mu, the x that, the x delta, okay, exactly, which is what I'll be expecting. I'll be obtaining this expression right here, as you can see. So in order to avoid being redundant, we can just look up the expression and look at and take it up. So this expression is what I will be expecting. This being equal to that. That's by multiplying by the inverse of this. So we can identify, of course, in this expression that we've obtained in our first step, that this is already the same as what we have here written out. And of course, to help us move on quickly, we can see also at this point in time that this is the same as that. Of course, we could have written this, obtained this from here. It's just a matter of saying that here I have mu, and then here I have, okay, gamma is the same for both of them. All I need to find is where mu occupies. Mu was the only one here, it's not a dummy index. So for nu also occupied a position there, not being a dummy index. And so the alpha beta here, gamma alpha is given here, gamma alpha. So it means gamma beta here also, gamma beta takes that position. and of course the dummy indices. For the sake of uniformity and ease of evaluation, we have maintained the same dummy indices for the two expressions, even though we could have chosen different dummy indices. So in other words, what I'm going to do next is simply to take the expression for this here and put here, yes, and that for this and put this there. So in my next step, I have that G alpha beta comma gamma. We need to put that in a better. So this is G alpha beta comma gamma being equal to here, and that is what we have here. So this is going to be gamma, which is our affine connector, alpha, and I have here with me the x prime mu, the x delta, and of course the other differential that is there along the line, the x beta, G here, mu prime plus. Looking again here, of course, so just to make things to go in order, I'll write this first, delta, gamma, beta. So the next thing I'm going to have there is the s prime mu, the x here, alpha, and what follows it here is the x prime nu. Here, this is going to be the x delta. And so what I've got here is G mu nu prime. Okay. They're beginning to look much like it. Of course, looking at our first transformation, which is this here, we can already see that this here is beginning to look just like what we had initially. So we just have to make the identification of the indices and see what to call them. We had a covariant vector over there, covariant tensor being equal over there to some expression relating it to another covariant tensor. So what we are going to have there is some G. So you can see this is mu nu. So we expect that this, for instance, so coming over to this side of the board, G alpha beta comma gamma is equal to, here we have our affine connector, gamma delta, gamma alpha, but then this becomes G, subscript here becomes delta beta. That is what we have, as you can see. And of course, judging from our expression of this here, alpha beta, alpha beta. So what we have here is delta beta, and that's what takes over there. Now here I have alpha delta. So this is plus an affine connector of delta, and here I have gamma beta, of course. No. Yeah, exactly. That's what it is. So, but now my G would be G here, some alpha delta. Now, I believe this was one of the expressions we obtained last time, of course, by combining two Christoffel symbols with the kind of expression that we have used. So we sort of kind of used the expression we intended to derive. Well, let's just keep going and see what it turns out to be later on for us. At this point, of course, it becomes clear because, of course, if we were to define the covariant derivative of this with respect to gamma, what we'll do is to say differentiate the whole tensor itself. First of all, with respect to gamma, then minus some contraction. Let me use, n for that contraction. Gamma is that, and what I'm contracting in this case is alpha, and this is n and beta, and I'm going to have another one again. Let me use m this time around. Gamma still follows, beta is what I'm contracting, G alpha, and this is m. And of course, you can see that these expressions here for alpha and beta are just the same as the ones here, because this is the dummy index. This delta here might as well be the n, and this delta here also might as well be the m's. So you have gamma beta, and you have here also delta beta. Like I said, it could have been the delta beta, but gamma alpha. So what it means here is that this expression is what we have here. And so you can see that if we were to plug this into this expression, we end up with our old friend, that the covariant derivative of the metric tensor is always 0. Anyway, this is just a side. But then the very crucial thing is here, we can, just by looking at this expression, rewrite it for different indices, because in the end, one operation that is going to be very crucial to obtaining that result will be this. performing this plus this minus that. So I don't have to go through all the first step all over again. I already have G alpha beta comma gamma. Now what do I do to get what is it called? G gamma beta comma alpha. All I have to do is to, as you can see, I just need to interchange alpha and gamma. So if I am to do that, I have to leave the deltas alone. That's not what concerns us here. Alpha and gamma, well then, we have alpha, we have gamma. The Christopher symbol there remains unchanged. And delta and beta, nothing happens in the first term. Alpha and gamma, again, we leave the deltas alone, but the gamma here becomes alpha, beta, G, and the alpha here becomes gamma, delta. And that is the expression for G, gamma, beta, comma, alpha. Now, for the case of G, alpha, gamma, comma, beta, of course, depending on how we want to do this, we may decide, no, this isn't that ideal because I will have to interchange alpha and beta. Okay, alpha and gamma, afterwards, then interchange beta and gamma. Well, so straightforward from the very first expression. You can see that all I have to do in this case is to interchange beta and gamma, and I have this. So just looking again at the first expression, interchanging beta and gamma. So I'm going to leave alpha wherever I see it and the dummy indices alone. Gamma is what I have here, so it becomes beta. Alpha again is to be left alone. The delta there should be left alone because the dummy index. Okay, now so the beta that is here becomes a gamma because that's what we intend to do, make that interchange plus. Here we have again the affine connector. This is a dummy index, the delta is to be left alone. And the gamma over there becomes a beta, and the beta becomes a gamma. And I guess this metric tensor here remains just untouched. So what do we intend to do next? Perform this operation. G sub alpha beta comma gamma plus here G gamma beta comma alpha minus G alpha gamma comma beta. What is this going to give us? So it simply means the first expression plus the second one minus the last one. Yeah, of course we know what this is going to lead to. And you can see while we're looking at this, we know that this last expression is going to have the minuses, while these ones are going to remain plus. So we just need to look and see which one of these will cancel with any one at all. So I have beta gamma here with a delta beta gamma. Of course, these are dummy indices just happen to be the same, but alpha, alpha. So you can see I can label this 1, 1 like this to denote that they cancel both. I have beta alpha here. I have alpha beta. This is the same. It's a dummy, not necessarily dummy, it's symmetric. The affine connector is symmetric with respect to the lower indices. The important thing here is also I have a gamma here. Even though it's gamma delta here and delta gamma is also symmetric for the metric tensor. The same dummy indexes, even if they were different, it will have been the same. So I could label these two and these two. So these two cancel. You can see what cancels what. So by the end of the day, you can see that the last expression, which was supposed to have the minuses, disappear. What I'm left with are these expressions here, which have plus with them still. Delta, gamma, alpha, G, delta, beta, plus here, I have delta, alpha, gamma, G, delta, beta. And these two expressions are just the same. You can see, even though I have gamma, alpha here, alpha, gamma is still the same. Delta, beta is still the same. So what I've got here is 2 times here, G, delta, alpha, gamma, G, delta, beta. Now, of course, it simply just means here that I could multiply. In other words, what I've just shown is here, G alpha beta comma gamma plus gamma beta comma alpha, and this is the same thing as not some minus. This is 2 times G delta beta. I just want to put it in that way, alpha gamma. Of course, the inverse of G delta beta is the same thing as G delta beta. So I'm going to multiply both sides by that inverse, right after dividing both sides with respect to 2. So it means that I have here with me alpha gamma equal to 1 all over 2 G delta beta multiplying this. So it's kind of funny, right? Because in the last presentation, we had to do a lot of algebra, something far more involved than this to obtain the same expression. So, well, I guess it's still a landmine achievement, and this is how physics works actually. It depends on what you call, so there is always, usually most times, a quicker way to get to a solution, regardless of what problem you're solving. So it's usually a matter of your approach and how easy you get. So in this case now we can see that it was quite easier going through by this procedure. Okay, now looking at one other property, a property that we have often used but haven't actually shown in this series, that the covariant derivative of any scalar is just the same as its partial derivative. Of course, one of the problems why, one of the reasons for this is usually if you consider a scalar, it's just a scalar. It's not some, well, it's a tensor too, but a tensor of 0 rank. It doesn't have any index with which you want to contract with the affine connectors or the Christoffel symbols. So usually, for instance, if you were to have a vector, if you have a vector A, alpha, and you want to take covariant derivative with respect to gamma, and like we said, the rule is always differentiate the whole tensor with respect, just partially with respect to that, but since is here an upper index, you have plus. I'm going to contract this, for instance, here with something lower n, and this is n. What I'm contracting moves over here, what I'm differentiating with respect to, and that's it. So there's an index on the vector or any tensor whatsoever that you want to use. But the case here is not the same for a scalar. You don't have any index on a scalar. So when it comes to this step, what do? Okay, well, now we have another way, a very smart way. Okay, so I guess at this point I should make this mention. I've already mentioned the book by Charles Misner, Kipton, and John Archibald Wheeler, Gravitation, and also Gravitation and Cosmology by Steven Weinberg. Now another book again is Supergravity, Supersymmetry and Unification by Frank Nat. Particularly the chapter 2 of that book should be very useful. And like I said, I'll try my best to keep giving you the names of the books as we find them relevant in our presentation. There are a plethora of books on generality of relativity out there. I don't want to start making a list. Otherwise, I guess I probably wouldn't finish. Well, a simple idea here is quite smart actually if you ask me. We do know from vector analysis that when you take the dot product of two vectors, you get a scalar. Yeah. You take the cross product of two vectors, you just get another vector, and that's what it is. The dot product of two vectors is a scalar. And we denote that dot product usually may say something like a sub I, ai. In this case, it means a squared. Or you can say a sub I, bi, and it simply means ab, and that is a scalar. So you can see that given the fact that a scalar itself may not have an index, but when you consider it as a dot product in this form, we now have indices. So what do we do in this case? It therefore means that when we suggest the covariant derivative of this with respect to some delta, for instance, this is just the same thing as saying P alpha, Q alpha, covariantly differentiated with respect to X delta. And of course, we have already said that, again, this is something we haven't shown rigorously, but you can take my word for it. Covariant derivative obeys the Leibniz rule. So this time, again, I treat this as a constant, alpha, and that is delta. And so that is what we get. Now, at this point in time, you can see that what we have here is, looking at this expression, we can easily deal with these two. First of all, we have the covariant derivative of some contravariant vector or tensor, and then the covariant derivative of a covariant tensor over here. So now this, for instance, becomes the very first one, the P alpha, the X delta, and what have I got here? what I've got is going to be plus a gamma. I'm contracting. Okay, let me see. Well, I can use anything, just whatever works. Sorry about it. So I can contract that with, so what we are contracting is this. Let me use n. It doesn't matter again, as we always say, Pn here. What I'm contracting is alpha. It simply joins that, and the delta is here. I'm multiplying it with q sub alpha. Again, plus here p alpha multiplying simply the q alpha, the x delta. But it will be taking a minus sign. I am contracting the alpha. Let me just use n for the sake of uniformity. I mustn't use that, but now the alpha joins the affine connector and the delta is over there. And this is what we get. So this is just usually what you will expect. Now what we get finally is to say here the p alpha, the x delta times q sub alpha plus gamma this and I have here alpha Pn q sub alpha plus here p alpha, the q alpha, the x delta minus gamma alpha delta n here p alpha qn. That's what you get.